Hi everyone, this video is going to be a little different. This isn't going to be a how-to video, but rather this is going to be a review of some of the technical things behind the scenes with SkyTrack, mainly around the different commands that SkyTrack uses for tracking, and whether it be for tracking satellites or for tracking things like comets and such. I get quite a few emails from users wondering why their particular mount can't take advantage of certain features of SkyTrack, and also occasional emails from vendors as well, inquiring how they can enhance their ASCOM drivers to make use of all the features. So this video will serve as a reference to those type of questions. I apologize, it'll probably be boring to some because I'm going to do a lot of talking and not a lot of showing things on the screen, but if you're interested in the more technical aspects, it might be interesting to you as well. So Satellite Tracker has two different groupings of methods to connect and communicate with the mount, either through ASCOM drivers or what I've termed as legacy interfaces. And a legacy interface meaning that it's uniquely programmed to that mount using that mount's command language, which is sort of embedded, or not sort of, is embedded in the firmware of the mount. So let's first talk about ASCOM, and most of this video is going to dwell on ASCOM. So this is the home page of the ASCOM standards website, and we can see here around 2001 it looks like the initiative started, and what the initiative was attempting to do, and has done very well, was to set standards around interface definitions, and then also supply development and testing tools to support adopters of that standard, and support users and developers. And a real shout out to all those that volunteer their time to this initiative, because this ASCOM alone is responsible for the awesome technology that we have in the hobby of astronomy. So of course ASCOM is not just around mounts, it's around cameras, focusers, rotators, environmental devices, all sorts of devices that we use in astronomy. So basically what it's doing for a developer like me with a third-party application like SkyTrack, it intends to enable me just to develop one ASCOM compatible interface, which then communicates with various ASCOM drivers in a standard way, and then it's up to the developers of the ASCOM driver to communicate with those unique command languages for each mount. So it's supposed to make our devices very plug and play, and for the large part it achieves that well. The other thing to mention, there are two different flavors of ASCOM. There's what they're terming here as classical ASCOM, which makes use of the Windows COM method of interfacing, and then starting in 2018 we had ASCOM Alpaca, which uses more of a universal type of interface, and then easily supports different platforms other than Windows. SkyTrack uses the classical ASCOM because it is a Windows only application, and I may in the future look at supporting Alpaca as that gets adopted wider. So I know some of the terms I use in SkyTrack can be confusing, so I talk about satellite tracking, and satellite tracking is either leapfrog or what I've termed is continuous tracking, meaning it's smoothly tracking the satellite across the sky, keeping it in the field of view, whereas leapfrog is jumping ahead of the satellite, stopping, waiting for the satellite to drift through the field of view, then jumping ahead of it again. Normally when we think of tracking with astronomy, we think of tracking like sidereal rate tracking, and so I'm going to talk about that first. This is on the ASCOM standards website. So these are the 4 basic types of tracking rates. Well, they call it the well-known tracking rates. So sidereal rate is basically compensating for the movement of the stars across the sky. So that's counteracting the rotation of the Earth, and also the Earth orbiting around the Sun to some extent. And so we're all, I think, familiar with sidereal rate tracking. And then there's these other 3 common ones they mention. Lunar rate tracking, of course, tracking the motion of the moon. Solar tracking the motion of the sun. And king rate tracking, which is basically sidereal rate tracking, but also accounting for refraction. So satellite tracking only uses sidereal rate tracking. It doesn't allow you to switch, like with your hand control on your mount. On a lot of mounts you can switch to these other types of, or within the ASCOM driver you can switch to these other types of tracking rates. SkyTrack only uses sidereal. It is possible to track the moon and track the sun, and very accurately, and probably more accurately than what's embedded in the firmware of your mount with lunar and solar rate tracking. And hopefully I'll remember to quickly show you that at the end. But I just want to mention that when ASCOM talks about tracking, it's talking about these tracking rates, whereas in SkyTrack, I refer to satellite tracking, which can be what I called continuous tracking or leapfrog tracking. And then there's also in recent versions a new feature tracking other objects in the sky like comets and asteroids and other slower moving objects and we get that data from the JPL Horizons website. And I refer to that in SkyTrack as custom tracking. So it's basically a customized sidereal rate. So it's slower stuff. It's close to sidereal, but it's a little different, and I just call it custom tracking. So in addition to these tracking rates, there's other types of movement features in ASCOM. One we won't be talking about today, and that is pulse guiding. A satellite tracker, SkyTrack does not use pulse guiding at all. But the other 2 main types of movement in ASCOM one is called the move access method, and then we have 2 different rates that we can adjust the properties to, and that's the RA rate and the declination rate. And SkyTrack uses all 3 of these in different areas. So they differ. Move access method is more of a movement in terms of the mechanical axes of the mount, and so it's not in relation to any coordinates. It's just mechanically moving the axes on the mount. The RA rate and declination rate, they are in terms more of the equatorial coordinate system. So in an alt-az mount, for example, if you're changing the RA pointing position, you're actually moving both mechanical mounts. And even in an equatorial mount that's been star aligned and calibrated, your mount might not be perfectly level, so to change RA you might have to adjust declination a little bit. So these rates can affect both mechanical axes of the mount. So that's the difference. I tend to view, and hopefully I'm right in this. I think I am. That move access method is a better method of slewing the mount, or when you're tracking something that's moving relatively fast. So a low Earth orbit satellite, I would say, is something that's moving relatively fast. And so in SkyTrack, when we're tracking satellites, it's using the move access method in ASCOM. RA rate and declination rate, I think, are more fitting for slower moving objects, and one of the reasons is because of what they're actually doing is that they're setting rates as an offset. Right there it says provide support for offset tracking. So in the case of RA rate, it's setting that on top of that sidereal rate in which the mount is already tracking. And so I think it's more fitting for objects that are in the same ballpark of sidereal rate in terms of tracking. So that would include asteroids, comets, are in that ballpark of movement. So I said SkyTrack uses move access for satellite tracking, and one thing to note, let's find a satellite that's higher up. And I'm just going to connect to the ASCOM simulator. And we're going to start tracking that. As a satellite moves across the sky, it's going to be moving at different rates relative to the viewer. So different angular motion rates. It's going to generally be a lot slower when it's low in the sky, and as the elevation increases, it's going to start moving at a faster rate, and then it's going to start slowing down again as it goes lower in the sky. And of course, it depends too on which mount you're using. So if we're using a equatorial mount, as it gets close to the pole, you can see RA changes really fast. And if we had an alt-az mount, as we get close to the zenith, we can see the az axis is going to have to move really quickly. But regardless of what type of mount, the satellite is constantly changing its angular velocity as it goes across the sky. And so what SkyTrack is doing about once every second, or 1500 milliseconds or so, it's looking at the current rate that the satellite's moving, and it's adjusting those that move access rate to exactly what it needs to be. It's also doing this in a closed loop manner, so that means it's asking the mount, okay, mount, where are you? Satellite, where are you? I'm currently off by this much. So it's applying a little offset to the calculated rate of the movement of the satellite to try to recenter it. And you can see this value down here in the corner is constantly updating, trying to keep that satellite centered. And that's going to be important too, and I'll show you some of the difficulties around that in a second here. But the move axis command takes a rate for each axis, so we can move each axis at a different rate, and that rate is degrees per second. Now, different ASCOM drivers have implemented this differently in terms of what rate it can accept. So some mounts can accept quite a variable rate between a minimum and a maximum, and other mounts have a set of preset rates, and it can only accept those preset rates. And we can see that. So I have some, this is an excerpt from a log from SkyTrack. So when it first connects to the mount, it takes a look at that. And so first thing it asks, for each axis, how many rates do you have for that axis? And a rate meaning a minimum, a set of a minimum and a maximum rate. So in this case, it says there's only one. The minimum rate is 0. The maximum rate it can slew is 5 degrees per second. So because this minimum and maximum are different, that means I can choose any number between 0 and 5. So if I calculate that my satellite is moving at 0.124 degrees per second, I can tell this mount to move 0.124 degrees per second. So any value with decimal points between 0 and 5, I can specify and it will accept and carry that command out. Here's another mount. So here's this mount. When I ask how many rates does it have for axis 0, it's telling me there's 9 different rates. And then it lists all 9 different rates. And you can see for the minimum and maximum value for each rate, the value is the same. So minimum 0.533, maximum 0.533. So if my mount is moving at, let's say, 0.45 degrees per second, or sorry, my satellite, I can't tell my mount to move 0.45 degrees per second. I can tell it to move 0.266, or I can tell it to move 0.533. And again, that's because this ASCOM driver only accepts preset values, a set of preset values for move access. Where on this one, I can tell it to move 0.45 because that is a value between 0 and 5. So that's the restriction that some ASCOM drivers have. And so when you select continuous tracking and connect to your mount, if you get a message saying it can't do it, it's not compatible with the continuously variable value for that move access command, this is probably why. If you looked at your log, you'd probably see that it has minimum and maximum values that are the same. So it has a number of preset values and you can only specify those. So that's not going to get you very smooth continuous tracking. You're not going to be able to keep the mount right on that satellite. So that's the restriction. In addition to that, remember we said that this tracking is going to be closed loop. So when we're tracking our object, it's continually looking at the difference between where the mount is pointing, where the satellite is, and adjusting that rate to try to make up that little delta and keep it as closely centered as it can. So that brings up another issue with some ASCOM drivers. And ASCOM continuous interface setup, this calibration routine that it does. So a number of reasons it has to do this calibration routine. We'll get into the second one in a minute, but I just want to point out number 7. It says check position, update frequency. So it's doing some testing on both sides of the meridian. And when the mount is asked to slew to the other side of the meridian, while it's slewing, what it's doing is it's rapidly asking the mount for its position. So what's your position? What's your position? What's your position? And it's expecting, because it's actively slewing and slewing at a fairly fast rate, it's expecting each value to be unique. Okay? But what happens is some ASCOM drivers queue that position. So they may only query the actual mount, read its encoders, and get the position about once per second, and then it keeps those values in a queue, and that's the answer you're going to get when you query it, rather than a live, up-to-date answer. And so we can see that too. So here is the log, a SkyTrack log from when it's doing that calibration routine, and it does sort of 3 sets of 3 in which it expects all these values to be unique. So at 11.612 seconds, it sent the query. this was the result. Then at 12.028 seconds, so that's roughly 400 milliseconds. It asks again, but it gets the exact same result as it did last time, even though the mount is actively slewing. And then at the next 400 milliseconds, you see finally we get a different answer. So this tells us that the mount is queuing that position. It's only updating it internally in the driver maybe once every second or something. But ideally what we want it to do is when we ask for its position, we want the driver then to go to the mount, read the encoders, and get the current position. So why does this matter? It's only a second. Well, if our satellite's slewing at 2 degrees per second, which is quite possible for it to be moving that fast, that means that the coordinates we get could be up to a second old. So in the case of 2 degrees per second, if the mount is slewing at that rate, the coordinates we're getting, where it says it's currently pointing at, could be up to 2 degrees off. And so that's going to be a big problem. So that's going to be a problem when we're doing that. Remember, we're doing that closed loop tracking here and trying to make up the delta. So what you're going to see then is you're going to see the satellite oscillating back and forth quite a bit in your field of view, because it's trying to make up a delta that maybe there really isn't. It's just that we're getting outdated information on the mount location. So let's look at another log here. So this is from a Skywatcher mount, and we can see the same point in the calibration here where it's testing that. And we can see now we're getting a different RA value each query. So we know from this then that the mount isn't queuing its position, and it's reading the position each time we query the ASCOM driver. So that's good. So this one I showed you that failed, that sometimes it gives the same position. That was actually from a Celestron ASCOM driver. So that was with an X-Star mount using the Celestron telescope driver. Same thing happens with CPWI, the software from Celestron. And I've made a request to them, and hopefully they can change it at some point in the future that it'll actually go back and read the mount encoders and give you an updated position. But that's one of the reasons why I do have these legacy interfaces. So you'll see there's a lot of legacy interfaces for Celestron in here. So thankfully with their command language, when you query the mount for its position, it'll give you an up-to-date position. The firmware itself on the mount doesn't queue it. So that's good. So that's the main reason why I have legacy interfaces for Celestron, is because they don't give you that real-time information. So that's satellite tracking using the move access method. The other, I'm going to talk about another problem with move access in a bit, but I want to first touch on, again, RA rate and declination rate. So where SkyTrack uses these is underneath the JPL custom tracking. And again, custom tracking is a phrase I use, a sort of a customized sidereal rate tracking. And we'll just connect here. And I've downloaded these earlier from the JPL Horizons website. There's another video on more of that and how to do that, but I'm not going to get into that in this particular video. So if I choose the comet and slew to it, what'll happen is I'll I'll go to where the comet, exactly where the comet is in that moment of time when I click slew to, and by default SkyTrack is just going to do sidereal rate tracking. Might be okay. It depends how fast the comet is moving. If you're imaging, it depends on how fast or how long of exposure you're using. If the comet's moving fairly fast or your exposure is fairly long, it's going to smudge in your image. So we have the option of doing this custom rate tracking. And so if my mount is capable of, and we can tell that from here after we connect through ASCOM, it'll list the ASCOM capabilities for the ASCOM driver. So if this can set RA rate and can set DEC rate, says yes, then we can use that feature. And this control will be enabled. If the mount can't, this is going to be grayed out. So as soon as I click that, what it's going to do is it's going to start applying this RA rate and DEC rate on top of sidereal rate time. So it's like a custom sidereal rate. And now we're going to track right to this comet. So if we did a longer exposure on it, the head of the comet, the nucleus of the comet should be nice and tight, but we might see our stars being a little streaked because we're no longer tracking right at sidereal rate tracking. Another problem I've seen is if we look at the specs here, so for the declination rate tracking, the units that this property is expecting is arc seconds per SI, so like a standard second. Okay, so arc seconds is an angular measurement. Okay, the RA rate is expecting something a little different. It's expecting seconds per sidereal rate second, so that sidereal rate second is just slightly different than a standard second, but a big difference is this. So this is a measurement of time as opposed to an angular measurement. So RA is in terms of hours. So like in a complete circle, let's say, in RA that's 24 hours. Where with declination, that would be, or in angular measurement, that's 360 degrees. So the difference between 24 and 360 is a factor of 15. So in 1 RA second would be 15 arc seconds. So that's quite an important difference. Unfortunately, some drivers are interpreting RA rate as arc seconds and not RA seconds, and so the tracking is going to be off by a factor of 15. And you can see here I have an option to use arc seconds per second for RA rate. EQ mod for Skywatcher's mount is one example. They are incorrectly using arc seconds. So if you're connecting with an EQ mod driver, then you need to click this. But you see, if I click this now, you're going to see my my delta in RA is going to quickly go wonky. So that's custom tracking rates. Earlier I said SkyTrack doesn't use lunar or solar tracking. In other words, setting that setting on your mount. And the reason is because you can do that here. So I could go to the moon here and enable custom tracking rates, and it's going to very accurately track the moon, and probably more accurate than what's built into the firmware of your mount. Again, it's using this very accurate data from the JPL Horizons website, and it depends on your mount too. I have a mount that has absolute encoder, so I can really accurately track the moon for long periods of time. And this might be important if you're imaging the moon or observing, at a long focal length, so a really high magnification, looking at a little cluster of craters or something. It's not going to wander at all over time if you're using this custom tracking. So this actually I found works better than what most mounts have built in for their lunar tracking. Okay, so if your mount doesn't have, if you connect to your mount and you see here it says no, it doesn't have these abilities in ASCOM, there still is another way that SkyTracker has to connect or to do that type of custom tracking, and it's using PhD2 guiding. And so we can connect to PhD2, and it has a cool little feature called comet tracking. It says comet tracking, but it can actually be used for other objects as well. So it could be used for tracking asteroids or other slow-moving objects. And so if you're not familiar with PhD2 guiding, what it does is it optically guides your telescope off of a star. So you got an image here of a star, and as it sees that very accurately, as it sees that star shift or move, it adjusts the mount used through that other ASCOM method of moving the mount called pulse guiding that I mentioned at the beginning. And what it does is when you set it custom rates, it'll purposely move away from those stars by those rates. So it actually works quite well. So I can show you here on the moon if we enable these rates. So the units are different again than what we were using before, but it's arc seconds per hour. So it actually will continue to update PhD2 with those, and PhD2 will allow the star that normally it would guide on to drift at this rate, and the effect then is you're guiding on your object of interest. So that's pretty cool, and it works actually quite well. So one more complication in this, I think within the ASCOM standards, the direction of some of these movements, so move axis and rate ascension and declination rate, I think it's spelled out pretty clearly, and pretty clear that move axis is a mechanical movement of the axes, and that the other two RA and dec rates are movements in terms of the equatorial coordinate system. But unfortunately, not all drivers do that. In fact, a lot of drivers, or some drivers, that use RA rate and dec rate are still moving the mount in terms of mechanical and not the coordinate system. So the way SkyTrack compensates for that, again, is this calibrate ASCOM tracking. And so and with a German equatorial mount, it'll depend on which side of the meridian the mount is, or which hemisphere it's viewing. And so SkyTrack will slew the mount to point in the western sky. It'll do a move axis command with a positive rate, and then it'll observe which way the mount actually moves. If your mount can do RA rate and declination rate, it'll also check that. And then it'll move to the other side of the meridian, so it'll point to the other side of the meridian. And again, we already talked about that frequency update frequency that it checks. And then on the other side of the sky, it'll check the same thing again. It'll again move axis 0 with a positive rate, move axis 1 with a positive rate, and see which way the mount actually moves. And then the same with our RE rate and deck rate, if it has those features. And unfortunately, it varies amongst mounts, and that's why it has to do this calibration to see which way the mount is going to move. Currently, I don't think the ASCOM has a conformance testing tool, and currently I don't think it tests these directions. And there was discussion lately on the ASCOM forums that they may consider putting that in the next release of the conformance tool, and that would not make this calibration necessary. But right now, that's the way it is, and we work around this by having this calibration routine. So that's what it's doing, is making sure things are moving the right way, and also checking to make sure it's not queuing its position coordinates. So I think that covers everything I want to talk about. Sorry for some, this is probably boring stuff. For other nerds like me, this technical stuff is more interesting. One thing I'm going to quickly mention, though, because I haven't done very many videos because I haven't had a lot of clear skies lately, but a couple of releases ago there was this new feature for lock current framing, and what that is normally when we let's go to our comet again. So if I salute the comet and I enable custom tracking rates, what it's going to be doing again, this is closed loop tracking. By the way, you can make it open loop or closed loop. So in that calibration routine, if you failed step number 7, you might have better success by going to open loop tracking once you get to once you're close enough to the object. But what it's doing, it's gonna keep this object right in the center of the field of your field of view. So that might not be desirable for something like a comet, because you might have the comet head right smack center in your image, but you might be cutting off the tail depending on how wide your view is. So what you can do is, before you enable custom tracking rates, and as you're looking through your imaging camera, you can be adjusting your mount. And for instance, you might be putting the head of the comet up in the corner of your field of view so that you can see the entire tail then across your image. And so if I have this clicked before I enable custom tracking, what it'll do, it'll retain that current framing. And so when I click enable, you can see now we have some RA and deck offsets. So what it's going to do is it's going to track now the exact speed of the comet, but your frame is going to be offset by these amounts here in order to, if you wanted to frame that comet with the head up in the corner, and then you can see the whole tail, that type of thing. Another time it might be useful is if you're looking at the moon with a long focal length, so a high magnification, and your field of view is just, a little cluster of craters. If you don't have this lock on, as soon as you start custom tracking, it's going to move your mount again right smack center of the moon, not maybe your area of interest. So again, this being able to lock the current framing helps with that. So anyway, that's it. That's sort of a technical review of how SkyTracker uses ASCOM, and I hope that's interesting to some and may answer some of your questions why your mount can't do some of the things in SkyTrack. And if you have any other questions, just let me know in the comments, and hopefully I'll get some clear skies soon, and I can do some more how-to type of videos. But thanks for now, and I hope you all have clear skies.